Okay, guys, this is lecture 17, and today we're going to talk about three topics, if I have enough time: linear regression, least squares, and normal equations. Okay, let's start with the linear regression. The linear regression is essentially a sort of it's a problem. It's a mathematical problem that can be formulated as um, um, an inverse problem. So let's say that um, we have a bunch of data, and we want to fit a line. Okay. So you can imagine the y-axis as the data, and the x-axis as some other data. And so the model parameters that you don't know are the coefficients of these equations here. So y is equal m of x plus q. So m, or let's say ax plus b. So you want to find a and b such that your line fits the data that you measured. Okay. This is an inverse problem because you want to find the optimal a and b such that you minimize the error. And it is also a regression problem because you're fitting some data with some kind of function. Regressions are used a lot in economics, for example, because they want to fit data, historical data, and make predictions for the future. So in general, a regression means finding a parametric curve that approximately fits a set of data points. So let's think about a parabolic trajectory problem. So y is equal m1 plus m2t minus 1 divided by 2 m3 times t squared. So y of t is, so this is a parabolic trajectory. Now y of t is the altitude of the object at time t. And we have three model parameters. So n is equal 3. So m is a vector that includes m1, m2, and m3. And this is of size n times 1. So m1 is the constant. m2 is some slope. And m3 is the quadratic term. Okay, it is important to understand that the problem itself, the function itself is quadratic, right? Because it's in t squared. But the problem that we're facing is linear for the three parameters m1, m2, and then 3. Indeed, if you look at the equation m1, m2, and m3, um, they don't have any power. It's just power 1 for all of them. Okay. So now let's say that we have some kind of measurements. Say that we have m measurements. We call them yi because they're supposed to be the heights. And these are measured at times ti, where I goes from 1 to m. Okay? Then the inverse problem can be written in this form. So remember that the inverse problem was in the form d equal g times m. So m is the model, the vector of model parameters, d is the vector of the data, and g is the matrix. Okay? So now this is d1 dm, sorry, y1 ym, the measurements. I call them y simply because it's an altitude, so you think about that as the y coordinate in the Cartesian plane. And then the model parameters is m1, m2, and m3, right? So if you look at the equation, the coefficients, so y, let's assume that we only have one measurement. So the coefficient m1 and m2 and m3 are multiplied by, m1 is multiplied by 1, m2 by t, and m3 times is multiplied by minus 1 divided by 2t squared. So here I'm going to write 1 t1 and minus 1 divided by 2t1 squared. Now y2 is going to be exactly the same because the parabolic trajectory is the same, right? It's just a different time step. So it's 1 t2 1 minus 1 divided by 2 t2 squared, and then the last one is going to be 1 tm minus 1 divided by 2 tm squared. Now you don't have to do it. I'm going to do it just to prove it that what I did makes sense. If I do the product of the matrix product, matrix vector product, sorry, the first one, y1, is going to be 1 times m1 plus t1 times m2 minus 1 divided by 2 m3 t1 square m3, which is exactly the expression that we had for our parabolic trajectory. And then if I do y2, I'm going to get the same, but this one here is going to be computed in t2. And then the last one is ym, which is 1 times m1. You clearly don't have to write 1. You could remove that. I just wanted to emphasize what we're doing. Plus tm minus 1 divided by 2 tm squared sorry, this is m2 and this is m3. Okay, I got it. So again, n is equal 3, m is equal whatever you want in this case, depending on how many measurements you have. And then you have a vector y of observation, which is equal to g multiplied by the vector of parameters m1, m2, and m3. And what you want to find, so the goal of the inverse problem is to find M1 and M2 and M3 such that you match the data that you have. So when the regression model is linear in the unknown parameters, again, this is a parabolic trajectory, so the physical model is not linear, but the regression model is linear in the unknown parameters M1 and 2 and M3, then we call this a linear regression, or a linear, which is also a linear inverse problem. So this is a linear regression, and the linear regression is also an example of linear inverse problem. Okay, now we're gonna discuss the least square problem. So in this case, I haven't shown you how to compute M1 and M2 and M3. I'm going to show it to you. What I want to do right now is simply show you a set of problems that can be written as an inverse problem. So this one here is an inverse problem because if we know G, then, and we have some measurements, we can compute M1 and M2 and M3. Again, we haven't learned how to solve it. We just saw how to formulate the inverse problem. So now we're going to discuss least square problems, squares problems. So these are problems that that involve the norm L2. So assume that we have a collection of M measurements. Which we're going to save in a vector D of length M. And say that using geological, geophysical model, physical models, we know some model G. So it's the physical operator or relation that link the data to the model that we care about. So if we have a model M in the set of Rn, so the model is a vector of n components, then if we apply G, we can compute the measurements. Now, let's say that we can express, so G is also a vector. Well, it's actually a matrix. This one here, we're going to write it right now as n vectors that we call GK in Rm. I'm going to explain to you in a minute what this means, okay? So here we have the data. And the data are written as a matrix G times M. Sorry, here I should have used the notation G, the matrix. We said that this is a linear problem, so I wanted to make it a little bit more general, but let's stick to the simple case. Okay. So now if we write this one here as D1 dm as usual, this can be written as G times M1 Mn. Okay. Okay, well, now in order to make the product, G must have dimension m times n. So this one here can be written as G11, GN1, GM, 1N, GM1, and GMN. Okay, now we're going to call each of these column vectors as G1. We have n of them, so this is G1, G2, Gn. So if we write each column as a vector, this is what we get. And each vector has dimension, so each gk, for k that goes from 1 to n, has dimension m by 1. Okay, well, then we know how to compute di for I that goes from 1 to m. Each of these di can be computed as the I row of G times m. So di for I that is 1, 2, until m is, so di is equal gi times m. Where gi is a vector and m is a vector. Sorry, this is, I used a confusing notation. Let's let's write it in words, which is easier. Otherwise, I will have to change the notation and it's going to be complicated. The I is the dot product of the I row of G times m. Which means that you take each element of the ith row in each column and you multiply by the components of m. So this means that D can be written as, which is equal to Gm, can be written as the sum for k that goes from 1 to n of Gk, the vector, times Mk. Again, where G is equal to G1, G2, Gn. And these ones here are the column vectors that compose the matrix G. Okay, so finally we formulated the problem. Now what we want to do is we're looking for a model that I'm going to call the, we want to find the model that I'm going to call M hat that minimizes the so-called residual vector. The residual vector is simply the vector R, which is D, the data that we measure, minus the sum that goes from 1 to n of gk times mk hat. So these ones here are the data that we measured, and these ones here are the predictions of the model. We do not expect to have an exact fit, so there will be some error. So we use a norm to measure the residuals. So what we want to do is compute the norm of R, which is equal to the norm of D minus GM. So we're going to use the norm L2. So this one here is equal to the square root of the sum for k that goes from 1 to m of R2, sorry, of RK power 2. Okay, this seems extremely complicated, but in practice it's much simpler. Once you figure out, you will see that the main issue is how to write the matrix G. If we can figure it out, then solving the problem is simple. Essentially what we're trying to do is we have a model that can make some data prediction. So no matter which M I plug in, I'm going to get some data predictions. Now I'm going to compare my data predictions with the actual data that I measured, and I want to minimize the mismatch. So let's think about the linear regression that we discussed earlier on. And in this case, we take a straight line, okay? So I have a set of points. So the only thing that I have to do for a linear fit is to guess two parameters, A and B. Let's say that I don't know anything about inverse theory, so what I'm going to do is I'm going to plug in some random numbers. Well, not completely random. I know that I look at the data and I guess that the slope should be positive because if x increases, y increases too. And we know that b is the intercept, so it looks like it would be something close to 0, okay? So I'm going to plug in some numbers. For example, I start with a equal 1 and b equal 0, and I get something like this. Now, it's not too far away. I didn't predict anything. You know, if I go completely random, I would get something like this maybe, but that doesn't make any sense. Yeah, I knew I was gonna mess up, but anyway. Okay, so I plug in some random numbers and I get this fit. I plug in some other random numbers and I get this fit. Well, I keep changing the numbers a and b until, which are my model parameters m, until I get a decent match. So what I'm minimizing is the errors between the points and my line. Okay? So if I look at the first one that I guessed, I think it was this one here, or let's draw another one, all the points are below, so there are going to be some points where the errors are big. Instead, if I look at the last one that I drew, I'm going to do it in green, well, some of them are above, some of them are below, and so this gives a better fit. So the straight line, by plugging in a and b, gives me some predictions for each value of x, for example. I have some measurements, and I want to minimize the error. Okay? So we do not expect to have a perfect fit. We will have some error, but we want to make the error small. That's essentially what we're trying to do. And this is an example in the linear case. Or for a linear regression, a simple linear regression. Okay, let's do an example that I hope is gonna clarify what we're trying to do. So the mean value. Well, as you can imagine, what we're trying to do is we're going to try to quantify some mean value for some data. Okay, so we have m measurements of the same quantity. And we collect them in a vector of data, D. So it's going to be D1, D2, Dm. Okay, well, we usually write it as a column vector, so let's do the usual notation, D1, Dm. Okay, so what we want to do is predict the mean value of the measurements. Well, we have seen enough about statistics to know how to compute the mean value, right? So I'm going to call this mean value m hat. Now, we have to define the residuals, like I did here. I should have highlighted this part because that's the key. So the residual here, the residuals, are defined as, so for I that goes from 1 to m, I'm going to define the residual Ri as di, my measurement, minus the mean value. Okay. Well, now we know how to we already know the solution of this problem, right? We're going to pretend that we don't because we're going to solve it using inverse theory rather than statistics. But we know the solution. If we apply statistics from statistics, I think it was lecture 13, maybe. No, maybe lecture 10, maybe. Anyway, so m hat would be d1 plus d2 plus dm divided by the number of measurement m. So we can write it as 1 divided by m times the sum for I that goes from 1 to m of di. Okay? Well, now we're going to use the L2 norm. So we're going to write this expression here, and we're going to try to minimize it. Okay, so the goal is to minimize the norm of the residuals like we did here. Okay, now if you remember the definition of norm, there is a square root of L2 norm, there is a square root. So we don't want to do a minimization problem with the square root, so we're going to minimize the L2 norm square. This is just to avoid to deal with the square root. It doesn't matter because the minimum of this one here, these two problems are exactly the same. This is equivalent, okay? Okay, let's write it down first. So we have the norm L2 square. This is equal to the sum for k that goes from 1 to m. Well, I used I before, so let's use I, of Ri squared. But we know the definition of Ri is just the difference between the data and the model predict and the and m hat. Okay, so this one here is a sum for I that goes from 1 to m of di minus m hat. Again, we don't know m hat. This is what we want to find. We're going to find it such that the R2 norm the L2 norm of R is going to have the minimum value. Well, this one here is just the square of a difference, so we can do it pretty easily. This is the sum for I that go from 1 to m of di square minus 2 m hat di plus m hat square. Now we can split this one here in three parts. This is the sum for I that goes from 1 to m of di square minus 2. M hat doesn't depend on I, so we can take it out. So we have the sum for I that goes from 1 to m of di. And then we're summing m hat square m times. So this is going to be m times m hat square. Okay, so this is the sum of m hat square for I that goes from 1 to k. To m, we do it m times, so this is m times m hat square. Okay, so this is the expression. Now we want to minimize the residual. So minimizing, well, we have seen the review of calculus, so this means taking the derivative with respect to the model m hat and set it to 0. So minimizing the norm L2 of R square means taking the derivative with respect to m hat of this quantity here and set it equal to 0. So this means that we have to take the derivative in m hat of this quantity that we wrote here. So this is the sum of di square minus 2 m hat, the sum of di plus m hat square. And we're going to set it to 0. Okay, so the derivative is linear, so we're going to do it piece by piece. So this is the derivative in dm hat of the sum for I that goes from 1 to m of di square. Now this one here is a constant. It doesn't depend on, well, I should say it does not depend on m hat. There's no m hat in the expression. So it means that the derivative is equal to 0. So this one here is going to be 0. Then we have minus the derivative of this expression here. Now, the derivative of m hat, of a constant times m hat, is the constant itself. So, because the derivative of m hat is 1, so this one here is going to be minus 2 times the sum for I that goes from 1 to m of di. And then we have plus the derivative in dm hat of m times m hat square. Everything has to be equal to 0. Now, the derivative of m hat square is 2m hat, and then there's the constant m. So this is plus 2m m hat equal to 0. Okay, now this is simple to solve. 2m m hat is equal to 2, the sum for I that goes from 1 to m of di. Now, we can simplify 2 and 2, and then m hat is equal to 1 divided by m times the sum for I that goes from 1 to m of di. But this one here is exactly the definition of mean that we know. So if we compute the mean of a bunch of measurements, and we, as a solution of an inverse problem, where we minimize the difference between the measurements and the predicted mean, well, the solution is exactly the definition of the sample mean that we know. So this means that um, the sample mean that we studied in statistics is the result of a least squares inverse problem, or just problem, for the measurements. So remember that we discussed. I'm not gonna show you the derivation, but remember that we discussed the mean and the median in statistics. Well, if you take the measurements and you minimize the norm, the L2 norm of the residuals, you obtain the mean. If you take the L1 norm, you're going to obtain the median. So this is like an interesting link between inverse theory and statistics. So if we take a bunch of measurements with the usual vector, okay. Well, if you minimize the L2 norm of the residuals, we just proved that, you obtain the mean. So m hat is equal to mean. Where m hat is the value of m that minimizes the L2 norm of the residuals. If you minimize the L1 norm, then m hat is the median. It would be exactly the same. I might assign it in the homework. Instead of taking the square root here, you're going to take the absolute value, and then you're going to do the minimization, and you're going to obtain the definition of median. So if we choose another norm, in general, we obtain a different solution of the inverse problem. Okay, now we're going to write probably one of the most important parts of statistics. Oh, sorry, of inverse theory, of linear inverse theory, which is related to the normal equations. So the normal equations provide the general least square solutions. If you think about what we have done so far, well, in the first case, the regression, we simply set up the problem. We simply set up the problem, but we didn't solve it. We just said, well, we want to find the coefficient m1, m2, m3 that minimizes the mismatch between the measurements and the predictions of the model. We're going to formulate the inverse problem in the form d equal gm, which is the usual expression, but we haven't found, I haven't explained you at least how to find the solution. Now, for the least square problem, again, we set it up saying that we have to minimize the norm of the residuals, but we haven't done it except for a very specific case where the operator is simply taking the average of the measurements. Now here we're going to look at a general inverse problem, and we're going to try to solve it we're going to try to find a general solution of the problem. So we said that we take a problem in the form G equal D equal G times M. And what we want to do is find M hat that minimizes the norm of the residual R2 square, which is equal to D minus G M hat. Now, this is going to require a little bit of operations, so I'm going to try to explain it in a couple of different ways and see if I succeed. So if I take if I assume that I know M hat and I apply the operator G, what I'm going to get is going to be a prediction, which we know is not exactly the data, because in most of the problems we're not going to fit the data exactly. So when we apply G to M hat is going to be equal to D hat. Ideally, D hat should be exactly equal to D, but we might not find the parameters such that these are exactly the same. Now, if I take the norm of the residuals, the square of the norm of the residuals, this one here can be written as D minus GM hat transpose times D minus GM hat. Right? This is exactly the same as writing this one here. And this one here is going to be D transpose times D minus 2 M hat transpose. Well, I'm not sure how familiar you are with these rules, so I'm going to write it step by step. So this is going to be minus G M hat transpose times D minus D times G M hat minus, I don't have enough space. I'm just going to copy it exactly the same. So it's D transpose D minus G M hat transpose times D minus D G M hat. So this is minus and minus plus. It's going to be G M hat transpose times G times M hat. Okay, so this is D transpose times D. Now, when you take the transpose of a product, I'm going to write it here. This is M hat transpose times G transpose. But these two, they are scalars, so they can be summed up. So this is going to be d transpose d minus 2 m hat transpose times g transpose times d plus m transpose g m hat transpose g transpose g m hat. Okay, let me recap a couple of steps that you might not be familiar with. I'm going to write it in a different color here. If you have A times B, or no matter if one can be a matrix and the other one a vector, or two matrices, and you take the transpose, this is equal to B transpose times A transpose. So this was the step that I did right here. Now this step here, if you take M transpose times G transpose times D, this is a scalar. Look at the dimension. M is generally, well, we didn't write the dimensions here, but so D is M by 1, G is M by N, and M is N by 1. So the dimension of this guy here is 1 by N, which is M transpose, times N times M times 1. So if you do the product, the dimension of this guy here is equal to 1 by 1, so this is a scalar. Okay? And the same if I do D times G times M hat. I forgot the transpose here, that's why it doesn't work. Okay. If you do D transpose times G times M hat, this is 1 times M times M times N times 1. So this is 1 by 1. So these are two scalars, so they can be summed up. And so this is 2m hat T times G transpose times D. Okay, so if you, I don't expect you to remember the definition, the derivation. So if you're not familiar with some rules of algebra, of linear algebra, you want to forget it, I'm okay with that, as long as you're going to remember the final result, which you're going to achieve in a minute. But especially for students in grad school who do inverse problems, this might be important to remember. I shouldn't have written it in red because that's, well, this is what we want to do. And I'm going to write down the solution m hat equal 2, which is what I want you to remember. Okay, so now we have to compute the derivative with respect to m hat of the residuals. This is the derivative with respect to m hat of d transpose d minus 2 m hat transpose times g transpose times d plus m hat transpose times g transpose times g times m hat. And this one here is going to be equal 0. We want it to be equal 0 because we want to find the minimum m hat that makes the norm of the residual small, which means that our errors are small. Okay, so this means that I have to compute this derivative here. Well, the derivative of this part here is going to be equal to 0. The derivative of this part here is going to be equal to 2g transpose d, and the derivative of this guy here is going to be equal to 2g transpose g m hat. Because it would be like where working with m hat squared. So what we get is that 0 minus 2g transpose d plus 2g transpose g times m hat is equal to 0. We're almost done. So what we get is 2g transpose g d equal 2g transpose g m hat. So we simplify 2 and 2. So we get g transpose times d is equal to g transpose times g times m hat. This is what we call the normal equations. So now we have to make an assumption. We have to assume that, so we assume that the inverse matrix of G transpose G exists. So now what we get is that we can isolate m hat, and this is going to be G transpose times G inverse times G transpose times D. Now, this matrix here, this is n by n. So it's a square matrix. It's also symmetric by construction. So this one here is n by n, and this one here is n by 1. Okay. For those of you who are not familiar with the inverse, I didn't cover that in the review of linear algebra. Probably I should have. Well, the inverse matrix of A is a matrix such that, so this is the inverse of A, is a matrix such that if you take A times A inverse is equal the identity matrix. And this is also equal to A inverse times A. Okay, so the normal equations seem to have no intuitive content. I mean, essentially, we're gonna try to find some sort of geometrical interpretations of the normal equations here. So they are derived from G transpose times G times M hat equal G transpose D, right? Well, so let's work on what we call the data prediction D hat. So if we take D hat, this is the data prediction for the model M hat. Well, D hat is equal to G times M hat by definition, right? So this is a linear combination of the GK vectors, where the GK are the columns of G. Now, let's assume that D hat well, sorry, let's assume that the vectors gk are linearly independent. Well, remember when we worked with matrices in the previous lecture? Um, well, we have seen some examples where, let's see if I can find it. Sorry, it was the one before that, I guess. Yeah, this one here. So this matrix, in this matrix here, A, the rows are not linearly independent because the third one can be expressed as twice the first one plus the second one. So the rank of A was not maximum. Now here in this lecture, we assume that the GK are independent. So we're assuming that the rank of G is the maximum rank that you can get. Okay. Well, now if I do a little bit of, if I play a little bit with these normal equations, I can rewrite this expression as G transpose times G m hat equal G transpose D. And now I can write G transpose G m hat minus G transpose D equals 0. And now I can write G transpose times G m hat minus D equals 0. Now I simply played a little bit with linear algebra rules, but now this one here is the definition of residuals. So these are the residuals by definition, right? It's the difference between, this is equal to d hat. So it's the difference between the prediction of the data and the predicted data and the measured data. So this means that G transpose times R is equal to 0. Where R is, I forgot the vector sign. It's much easier when you type it, because you can simply use the bold symbol. Anyway, well, this one here means that the residuals are perpendicular to G transpose because their dot product is equal to 0. So in other words, the normal equations in the least square sense means that if you take the columns of G, they are orthogonal to the residuals. So the residual, I'm going to give you the graphical interpretation in a minute, which is what I want you to remember, but the residual vector is orthogonal to every one of the columns of the column vectors of the G matrix. So essentially, we're making the residual perpendicular to the estimation subspace, minimizing the length of the residual. So we have here the subspace generated by G. Here we have, say, our prediction, d hat, the predicted data, d hat equal G times m hat. And then here we have our data, D. This is supposed to be in a three-dimensional space. It didn't come out well from my drawing, but I'm gonna exaggerate a little bit. my, okay, so this is the subspace of G. Then here I have the true data. So the residuals are perpendicular. So this is R and this is D. So the best solution is the one such that the residuals are perpendicular to the column vectors of G. So we are projecting the data D onto the column space of G. This concept is called the orthogonal projection of D into the subspace RG of RG. Sorry, this is my phone ringing. So this concept is called the orthogonal projection of D into the subspace generated by the columns of G, which by definition is the range of G. Such that the actual measurements can be expressed as D equal D hat, the prediction, plus the residual. So we have created a vector D hat, which is the orthogonal projection of D. Well, if you really want, for those who are actually going to do more inverse theory in the future, this is not necessarily required for the other ones. But there is a linear operator projector, which is the projection matrix. I'm going to write it as a note. Well, I guess this might be a little bit too much even for the graduate students, so I'm gonna skip that. Let me do an example, and then I should have 10 minutes. So this should be enough. You see that in practice it's going to be much easier. So this is the straight line fit. Which we're going to see in the last couple of weeks of the class that we can do easily with a computer software, but we can also do it manually. So the only thing the most important thing to remember here is just the normal equations and the prediction of the solution m hat using the normal equations. Now we're going to apply it to the straight line fit. So let's say that we have 3 measurements. So D is a vector in R3, D1, D2, D3. So for a straight line, we only need 2 coefficients, the slope and the intercept, or the zero crossing. So n is equal to, and then the model, so this is the number of model parameters of a straight line. I misspelled straight, I guess. So m is equal m1 and m2. Now, what we want to do is to formulate it in the inverse problem setting, D equal G times M. So we get that D1, D2, D3 is equal to G times m1 and m2. Well, this g is going to be pretty simple. This is simply 1 times x1, sorry, 1 and x1, 1 and x2, and 1 and x3 times m1 and m2. So where x1 and x2 and x3 are simply the coordinates where we made the measurements. So essentially the problem is we have 3 points, say here, here, and here. Well, doesn't look that great. So let's do it this way. So this is x, this is x1, this is x2. I'm going to move a little bit x3 like this. And then this is D1, D2, and D3. And now we want to find a straight line that's going to fit these 3 data points. So something like that. So D is equal m1x plus m2. Okay, which we can reformulate. So for each point, if you didn't understand, I'm going to explain again this part here if you didn't understand it. I might have gone a little bit too fast. So this is the equation of the straight line, right? Instead of y, I have x, I have d, but that's exactly the same. So d is equal m1x plus m2. Now this means that for d1, I have m1x1 plus m2. d2, it's m1x2 plus m2. And for d3, I have m1x3 plus m3. Now you might, plus m2. You might be more familiar calling m1 m and m2 q, but that's exactly the same. So if I write this is the matrix form, so this is going to be d equal d1, d2, d3, which is equal to m1 x1 plus m2, m1 x2 plus m2, and m1 x3 plus m3. Now this one here can also be written as 1x1, 1x2, and 1x3 times m1, m2, and m3. And this one here is equal g times m. Now if you don't, I think that the only tricky step might be from here to here. Well, if you try to do the math, again, we're going to do like we did before, first row times column. So this is going to be 1 m1 plus, plus x1 m2. I guess, I switched. I messed up this example. So this one here only have 2 components, of course. And I got the notation wrong here. So let me redo it 1 second. I'm going to explain it in a minute. Okay, so the straight line is d equal m1 is the intercept plus x m2. So d is m1 plus x m2. So the d1 is m1 plus x1 m2, m1 plus x2 m2, and m1 plus x3 m2. I switched m1 and m2. That's the mistake that I did, in case you're wondering. Okay, so now this is correct. So if you don't trust me, so m1 is the intercept or the intersection with the axis x equals 0, and m2 is the slope. Okay, so if you don't trust me on this step, we can do it. So we're going to do this one here times this one here. This is m1 plus x1 m2, which is exactly what we got here. This one here is m1 plus x2 m2, and the last one is m1 plus x3 m2. Okay, so the residual vector is simply the vector d minus g computed in m hat. And we know that the residuals, they must be orthogonal to the predictions. This is what our geometrical interpretation that we did before. So this means that if we have our 3 data points, so we have, let's say, D1, D2, D3, sorry. We have a straight line. This one here is the prediction d hat equal gm hat. So we're minimizing the orthogonal projections of the points on the straight line. So this is R3, this is R2, this is R1. Okay, I'm going to review this example one more time when we start next class, and then I'm going to make a link between statistics and inverse theory again. I'm going to show you that the maximum likely solution for the mean problem is exactly the same as the least square solution. Okay.